Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. So my name is Frank Marchis. I'm a senior researcher at the SETI Institute, and today we are going to talk about Asteroid in honor of the Asteroid Day. And for this, we invited Dante Loretta. Hi, Dante.
Hello, Frank.
Hello. So Dante is a professor of planetary science and cosmochemistry at the University of Arizona, and is also the PI, the principal investigator of the NASA Osiris-Rex Mission. And today we are going to talk about the Osiris-Rex Mission and the status of this mission, as well as the goal and objectives of this mission. It's great to having you here today, Dante, for the Asteroid Day. So
thank you. Yeah, it's always exciting when Asteroid Day rolls around. We love to raise awareness of the importance of studying asteroids.
Yes, most of your career has been about asteroids, so you have been doing other things in the past.
I actually started out as an analytical chemist and working on meteorites, which are fragments of asteroids that land on Earth. And we study meteorites largely to understand the early stages of planetary formation. So I went from being a laboratory chemist to studying rocks from outer space to deciding that we needed to go get our own rocks, and hence the Osiris-Rex asteroid sample return mission.
That's a perfect transition to explain the goals and objectives of the Osiris-Rex mission. So I just would like, before saying that, going to this few slides that you probably prepared, I would like to mention our viewers that they can start thinking about questions and ask questions on the chat. We will take the time to answer to your questions toward the end of this SETI Live. Dante, do you have some pictures, something to show?
Sure. So happy Asteroid Day, everybody, and thanks for the opportunity to talk about our Osiris-Rex mission. This is a program in NASA's New Frontiers mission line. New Frontiers are medium-class missions, and they target particularly challenging and scientifically exciting areas of the solar system. It's a partnership between the University of Arizona, NASA's Goddard Space Flight Center, and Lockheed Martin. And it's been an amazing journey on Osiris-Rex. We're targeting a near-Earth asteroid named Bennu. You can see some of the data illustrated on the cover of Science about our global mapping campaign. That came out in November 2020. So if you're really interested in the details of the characteristics of this object, I refer you to that work. And in the lower left there, I've got our timeline of what the mission has done at the asteroid. So we arrived back in 2018, going into orbit in 2019. And we spent all of that year mapping the asteroid in incredible detail. In fact, Bennu is now the highest mapped asteroid in the solar system, and actually the highest mapped object in terms of resolution. We've got the whole asteroid about 5 centimeters per pixel, including amazing three-dimensional data from our laser altimeter provided by the Canadian Space Agency. At the end of 2019, we selected a sample site called Nightingale, and then in October of 2020, we actually went in to collect the sample.
So this mission is dedicated to explore an near-Earth asteroid and to get a sample, right?
Correct.
But there is like thousands of near-Earth asteroids, like 20,000, even more now at the moment. So why did you choose Bennu? Why this one?
Good question. Well, there wasn't 20,000 near-Earth asteroids when we were making the target selection, which happened actually all the way back in 2005. That's how long we've been working on this program. So we identified Bennu, at the time it was called 1999 RQ-36. And it's a pretty fun story because other mission teams around the world were looking at asteroid targets. We know JAXA, the Japanese Space Agency, has a very active and impressive asteroid exploration program. And our colleagues in Europe, working with the European Space Agency, were also targeting asteroids for a mission called Marco Polo at the time. And so we all had our lists of the ones that we thought were the most interesting and challenging. And we wanted to, not step on each other's toes. So we were trying not to pick targets that we knew other teams were working on. Mm-hmm. And nobody was picking Bennu. And I looked at it, and the orbit is great, very Earth-like orbit, which means you can launch, rendezvous, and return home with a sample relatively easily, as easy as anything is in spaceflight. And also it was fairly large. We estimated around 500 meters, and that's the accurate diameter of the asteroid. And it was dark, which implied a lot of carbon on the surface. And that's one of our key objectives of this kind of mission, is to understand carbon and organic chemistry and pathways to the origin of life. But the one thing that was keeping it off everybody's list was the rotation rate was estimated at about 2.15 hours, which is really fast. So your surface is going to be moving quickly, and getting down and making contact would be a challenge. Fortunately, our astronomy lead, Carl Hergenrother, he said, I think that it's actually 4.3 hours, that instead of the one period, it was only half a rotation. And we did follow-up work, and we found that, it actually is spinning every 4.3 hours, which makes it a perfect target. And so we were able to claim it for the Osiris-Rex mission target and tell our colleagues, okay, this is the one we're going to. You guys go to one of these other asteroids that you're considering.
Yeah, that's a very interesting part, is that when you select a target, you pay attention to the orbit, because of course you don't want your mission to spend all its energy to go all the way over there and spend hours and years to go there. But you also choose a target which corresponds to your scientific goal. In this case, it's a dark asteroid, a C-type asteroid, or some kind of maybe dark surface.
That's right.
And for most asteroids, we don't know anything about them. We know it's a tiny dot moving in the sky, and we see a slight variation of light because they spin on themselves, and that's all. That's for most of them the case, right?
And you saw on that picture of Bennu, it's fairly spherical, right? I mean, some asteroids are like peanuts, they're really, and what we're referring to as the light curve, right? How it gets brighter and dimmer as it spins, and you see different parts of the area. But Bennu is very spherical, and so it doesn't change very much as it spins, which is why it was so hard for us to interpret that light curve. Was it 2.15 hours or 4.3 hours? We bet on the 4.3 hours, and that turned out to be the correct answer.
So before we go through the first results of the investigation with the mission, let me tell you that we have people watching us from the UK, from New Zealand, Christchurch, from Birmingham, from Stars from Suraf, Canada, Oregon, Australia, Athens, Greece, Brazil. So welcome, and today we are talking about the Osiris-Rex with the PI of the mission, Dante Loretta. So don't forget, if you have any questions, just write them in the chat and we will take the time to answer to you. So Dante, after this exploration phase, before we talk about the sample return, because people want to talk about that, I know, but tell us a bit what we learned about Bennu.
Well, I like to say Bennu is a trickster because it really literally threw some curveballs at us. So one of the things that we were trying to do with our ground-based astronomy was to characterize how rough the surface was, because we wanted to have a relatively flat area to send the spacecraft down to scoop up the sample. And I'll show you an animation in a little bit about how that technology worked. And Bennu looked really good. We had radar data, which told us about the roughness of the surface as radio waves bounce off. And we also had thermal data from the Spitzer Space Telescope. And there's a key property that we use to study asteroids called thermal inertia. And you're probably familiar with inertia as being resistance to change, right? Like Newton's law, if you want to get something moving, you have to apply a force. But this is thermal inertia, which means resistance to changing temperature. And something heats up, cools off very quickly. It's normally fine-grained like a beach. And if something heats up and cools off very slowly, it's like a big boulder. Bennu heats up and cools off very quickly. It looked like a beach, and I use the term beach all the time. I was like, it's going to be a beach. It's going to have sand all over the place. It's going to be super easy to get in there and scoop up our sample and get out of there. That is not the case. Bennu is totally rugged, rough, and rocky. And it was really an eye-opening experience when we got those first images back from the spacecraft. And then 1 week after we got into orbit, we saw Bennu's surface was literally exploding and shooting rock fragments into space. We were concerned that it was going to be dangerous for the spacecraft. And then this is where, your intuition about how things operate in microgravity fails you, because we saw these particles flying off and we're like, oh my God, we're going to get hit with one of those and it's going to damage a camera or something. And then you're like, well, they're moving at like 30 centimeters a second. So they're kind of just lofting off the surface and falling back. So they look dynamic in the images, but it's microgravity and everything's moving so slow. If it hit the spacecraft, it would be like, boop, right? It was like, oh, there's no risk to the vehicle here. And now we got a great science investigation to go understand where these things are coming from.
We're going to ask later where these things coming from, probably sure. But let's talk about the sample return. So that's the primary objective, right?
Correct.
To pick up a sample of an asteroid back to space, back to Earth. So tell us a bit how we do this.
Yeah, let's go back to our slides here. So when we were first planning the mission, and I was talking to the engineering team, I said, I want to land on the surface. I want to spend some time. We want to look around. We want to identify samples and scoop them or grab them with a claw or something like that. And we very quickly realized there was too many unknowns. And as we'll see, it was a good thing that we made that choice. And the engineering team came back and they said, landing is going to be risky. And space flight's all about mitigating your risk. They said the way to do it is with this touch and go approach. So this animation shows you how we solve the problem of getting to the surface and collecting a sample. You can see the orange curve is the trajectory of the spacecraft, and we're basically flying over the asteroid until we hit a region we call the checkpoint, and then we fire the engines, and that sends us down to our match point where we match the speed that the asteroid surface is rotating. And then we make a very brief contact with the asteroid surface and collect our sample during those few seconds when we're interacting with the material that we want to collect. And here's an animation of what the design is as we got close to the asteroid surface. You can see we've got kind of a disc-like object that we're placing. It's basically an air filter. And we've got bottles of nitrogen gas higher up on that robotic arm. And it's kind of like a leaf blower. We just blow the gas into the regolith and it pushes the gravel and the dust into that filter. We also just have contact pads. Simply by making contact with the asteroid surface, we'll pick up dust grains. And then once we were satisfied that we had sample, we put the entire filter into a return capsule and get ready to bring it back to the Earth. So I love that video because it shows you the artist's conception back when we thought the surface was beach-like. And so it really showed you that we were hoping for a nice smooth area. We worked hard for over a year to find a spot on the asteroid surface where we could collect a sample. And then on October 20th of last year, we made contact. And then here you can see what happened when that collector hit the asteroid surface and fired the gas bottle. So one thing to notice right away is, we'll play this through a couple of times, the original surface is pretty rough and rocky, although it was one of the smoothest areas that we could find. But as soon as we started to go down into the subsurface, it got much finer grained. And in fact, there, the beach-like sandy material, you'll see in some of these images coming up here, a lot of fine-grained particles in here. So the sand was there, it just was just under the surface. The other thing that was really amazing is that the surface basically behaved like there was no cohesion. Like we just pushed in, and if we hadn't fired our backaway thrusters, that spacecraft would have sunk all the way down several meters into the regolith, and we would have been stuck there probably like in quicksand. So the asteroid surface is not solid, it's fluid, and it really behaves like almost like water, and it just splashed away from us. And then we blew that gas and we made a huge crater in the surface of the asteroid.
I'm speechless because the fact that we landed something on an asteroid, I mean, for the young generation, for you, probably nothing, but for me, I do remember how we were questioning those thermal inertia data in the past, how we were like questioning the composition of an asteroid, and people coming to explain that we're going to be able to mine asteroid, and people saying, well, it's not that easy because we don't really know what those asteroids are made of. And this is a typical example of a big surprise. Like
that's right. A really big surprise. And asteroid mining will come into play here because we're talking about, it actually probably helps with asteroid mining that the surface is so fluid-like. You can push and move stuff around and process it for your commodity that you're trying to extract.
Okay, so now you have a sample.
Yes.
Are you 100% sure about that?
We are 100% sure. Yeah, we actually,
Okay.
we were able to see the sample inside the sample head after we collected the material. And we were able to constrain the mass that we collected based on various forms of analysis. I think I had it on the slide there. Let's take another look back at that. Right now, our best estimate is that we collected over 250 grams, that we stowed over 250 grams of sample. And our requirement or our goal for the mission was 60 grams. So we got more than 4 times the sample that we wanted to collect in that collector. And we have high confidence. There's about 100-gram uncertainty on that. So it could be as low as 150 grams or as high as 350 grams if our estimate of the uncertainties are accurate.
Okay.
And so with that, we were able to stow it. So I showed you the animation of what we wanted to do, but just a week later after tag, touch and go sampling, we were able to put it into the sample return capsule. And now we are basically on cruise control. We're heading back to the Earth. We fired our thrusters on May 10th, and there's very little activity that's required. It's an ultimate billiard shot. You know, we fire thrusters on May 10th of 2021, and that targets the Earth on September 24th, 2023.
So where the sample is gonna land?
The sample's coming into the Utah Test and Training Range, which is in the southwestern United States, just southwest of Salt Lake City, Utah.
Okay. So it's maybe too early to claim that it's a success, but it seems quite promising, right?
Yeah, we have mission success criteria, and we have checked off 3 out of the 5 right now. So we've got the sample. The next thing is to safely land it on Earth.
So how do you feel about that? What what were you doing when the spacecraft made the touchdown?
So on the day of sample collection, I was on air. I was the on-air talent for NASA's live broadcast. So I was on TV, and we were talking about everything that was happening, or interviewing different team members and stepping the audience through the whole sample collection event. So I was your host basically for the collection, because as the PI, by the time we get to actually implementing the command sequence on the spacecraft, my job is done. I've made all the decisions, and the team has gone through and made sure the spacecraft is going to do what we need it to do.
How long does it take basically to get those pictures? Someone asked that in our chat.
Yeah, at the time of sample collection, it was about 18-minute one-way light time. We were on the other side of the sun. So Bennu has a very similar orbit to the Earth, which is why it's potentially hazardous and maybe going to hit the Earth well in the future. But it was all the way on the opposite side of its orbit. So we had to send the signals not only from the spacecraft, past the sun, and then another astronomical unit to reach the Earth, and then a little bit more because Bennu's orbit is slightly eccentric.
Okay, so we have time to take questions, and while you think our audience is thinking about questions, I would like to thank people joining us from Toronto, Southern California, Denver, Colorado, Denmark, Vancouver Island in British Columbia. And where are you located right now, Dante?
I am at the University of Arizona in Tucson, Arizona.
I just would like to mention that I am not at the SETI Institute, and I'm not in San Francisco. Today, I'm at Unistellar headquarters in Marseille, France. So that's the reason you may hear some weird noise in the street. So we have questions. We have a lot of questions. So let me just compile some of them together. Oh, the question we had is about water. Did we find water on Bennu? What kind of analysis have you done to look for water, and what the significance of this result?
Yeah, great question. So I had mentioned that we had targeted Bennu because we expected it to be rich in carbon. And in fact, we have confirmed that there is large abundances of carbon compounds on the surface of the asteroid. And that's the same technique that we use to look for water. We use an instrument called OVIRS, which is the Osiris-Rex Visible and Infrared Spectrometer. And it's basically looking at sunlight that is reflected off the surface. And if there's a chemical compound that has a specific chemical bond energy, it'll actually remove some of the sunlight. And we can look for what's called an absorption in that spectrum. And Bennu is saturated in water. It was one of the first discoveries, even on the way in, before we officially arrived and we were on the approach trajectory. OVIRs turned on. Bennu didn't even fill one field of view, and we saw the water band very deep and broad, and it looks really exciting. My current best estimate is that about 10% by weight of the asteroid is water. That's really exciting for many reasons. Scientifically, we're interested in objects like Bennu, and did they bring organic material that may have contributed to the origin of life? But we're also interested if they made Earth a habitable world, and we know habitability is intimately tied to a hydrosphere. You want an active water cycle where you have oceans and evaporation and rainwater and runoff. That really, we think, is critical, at least for life as we know it. So that also feeds into our origins investigations to look at the origin of water. And then if you're interested in asteroid mining, and I've worked in this field for many years now, water is identified as the top economic commodity, which surprises a lot of people because it's abundant here on Earth, although not in Tucson right now. We're in the middle of a mega drought, so we could use some asteroid water. But you would not bring it down to the surface of the Earth. You would actually break it apart into hydrogen and oxygen, and that becomes rocket fuel. And then you turn Bennu into an interplanetary gas station, and you sell your water to your customers.
Thank you. Before I take another question, I would like to thank all the people who are having their birthday fundraiser for the SETI Institute. So thank you very much, Tim, Ray, Brent, Paul, Carl, Ed, Remy. Happy birthday, first of all, and thank you for helping our program of our outreach program with this birthday fundraiser. So one question: you mentioned that Bennu is having this kind of weird activity. Someone asked, does that mean that Bennu is growing or diminishing in mass? And what is this activity? Do we have any idea now?
It looks like Bennu is losing mass, so it's what we call an active asteroid. Some of these particles, when they eject off the surface, they are on an escape trajectory. And that's not that hard to do because the escape velocity at Bennu is about 20 centimeters per second. So it doesn't take a lot of energy to leave the asteroid surface. We've seen particles coming off as with velocities as high as 3 meters per second, so many times the escape velocity, and they're just part of the interplanetary dust population. Most of them, though, don't have that fate. Most of them are on very low velocity trajectories, kind of suborbital, where they'll just leave the asteroid surface and then immediately re-impact. But on occasion, they actually leave the asteroid surface, and then solar radiation pressure accelerates them. So instead of hitting the asteroid surface, they actually go into orbit, and they orbit around the asteroid. And we've seen hundreds of particles doing this throughout our entire encounter. This was a common phenomenon. It turned out to be a regular occurrence that these particles would eject. We don't know what's causing them. We only have theories right now. The leading theories are, one, these are actual other meteoroid dust particles that are striking Bennu's surface, and then it's just mini impacts. And we thought that that was unlikely when we first were evaluating the hypotheses, because seeing an impact is a pretty rare event. But once you get down to these really tiny guys, they're pretty common. Bennu should be getting hit by something with enough energy to cause a large ejection event every couple of weeks, just based on our flux models of dust in the inner solar system. And also probably contributing to it is the thermal stress, right? Bennu rotates every 4.3 hours, and it's very dark, so it heats up to 400 Kelvin and then cools off to 200 Kelvin at the equator every 4.3 hours. And that causes the rocks to expand and contract and expand and contract, and they build up stress energy, and they might just break when they get enough stress built up, or they might be activated. So even a very tiny meteor causes a large amount of particles. So those two influences may be working in tandem to produce the particle ejection. So hopefully there'll be some evidence in the return sample. I hope that we have some idea that something we brought home was one of these particles that was ejected.
Thank you. Thank you for this answer. Yeah, it's very interesting to see that asteroids are not those flying inert rock that we used to think about 15 years ago. Asteroids are mini geological worlds with activities and moons and rings, and so that's why they are fascinating, and that's why they deserve an asteroid day.
That's right. I agree. And they're fascinating. They're kind of a whole new realm of astrophysics, just trying to explain all those processes. because you basically take gravity out of the geologic equations and you're like, what's left to drive these processes on this asteroid?
Well, that's perfect transition for the question we had. We have like two identical questions about this liquid behavior. So what is this coming from? Is it coming from the composition? Is it coming from the composition, the size of the particle? How this asteroid is staying in one shape like that? What's the interpretation?
It's a good question. So it seems like it's only being held together by its microgravity. And the reason that it seems to behave like a fluid is that there is no indication of any cohesion between the particles. So what we thought is, as I mentioned, you pull gravity out of the equations that dominate like landslide mechanics or something like that. And it's the cohesion and the friction among the particles that acts as that binding force and prevents material typically from flowing in a completely fluid-like way. We do not have evidence of any kind of substantial cohesion on Bennu between its grains. I mean, when we were first modeling this, we thought the cohesion would be in the megapascals, millions of pascals, which is a measurement of the force between grains. And then we're like, well, maybe it's kilopascals. And now we're like, it's not even 1 Pascal. It's less than 1/1,000,000th of the force that we were modeling when we first started looking at these systems. So these particles just slide past each other. And that way, when you push on them, they just move out of the way. They don't stick.
So really like a fluid, but does he has a core? Do we know if he has a core?
Probably not. Our leading theory for the formation of Bennu is that it's a pile of rubble that accumulated after a much larger asteroid in the main asteroid belt was shattered in what we call a catastrophic disruption. So Bennu's like 0.5 kilometer in diameter, and we think its parent body was probably about 100 kilometers in diameter. So much, much larger volume. And so Bennu is just one little pile of the debris that was created from that extreme collision that's now wandered into the inner solar system. So it's probably just a bunch of boulders and gravel that are randomly accumulated together.
Thank you. We're having a lot of questions. I'm trying to put them together. So the sample return. So what's going to happen? The capsule is going to land on Utah. Someone's going to open the capsule. I think you may open the capsule, right?
Yeah. So we'll have a whole team. We're working with the United States military, so they'll be tracking the capsule as it comes in. It's the Air Force that controls the range where we're going to recover, and we'll have a whole series of helicopters with the ground crew, and I'll be on one of those. As soon as we know where the capsule is, we'll fly out there. We'll secure it. There's a few safety issues related to the battery and some of the pyro valves and things like that we need to make sure are safe. And then we'll eventually get it to NASA's Johnson Space Center in Houston, Texas, where right now we are building a curation facility to receive the samples. And it's there inside Houston, inside the clean room, that will actually open up the science canister, pull out the tag SAM, that sample collector head, and then, see what we got, and then start the science campaign for the sample analysis.
So who's going to look at this, and what? I know this could be a 2 hours conversation, and we have only 1 minute officially. So what exactly are you going to do with this sample? Who's going to work on this?
Yeah, it's really exciting time. We're developing the details of our sample analysis plan, and I've got laboratories all over the world that I'm corresponding with, talking about their capabilities and how they fit into our plan, which is very much hypothesis driven. We have a bunch of ideas about Bennu's history that we can test with analysis of the return sample. A lot of the work will be done in labs in the United States, including NASA laboratories at Goddard Space Flight Center and Johnson Space Flight Center. The Canadian Space Agency is a major partner. They contributed one of the key science instruments, and they'll get a bunch of the sample. And then across Europe, Australia, Asia, we've got collaborators lined up. Literally hundreds of investigations will kick off as soon as we can get material out of Houston and into their institutions.
Nice. So you mentioned briefly that JAXA has a mission, right? Hayabusa 2 that landed this year or last year.
They came back in December 2020. Yep, they came back to Earth.
So, and Ryugyu is also dark NEAs, right? So we're gonna have some kind of comparison between those two bodies.
Yeah, and it's been amazing. You know, you had mentioned at the beginning how unbelievable it was to those of us who've been working in this business that we actually got a spacecraft to an asteroid. Well, humanity actually got two spacecrafts to two asteroids and are bringing back two samples. One's already on Earth and one's coming back in 2023. And we're a tight-knit community, as you can imagine. And I'm a member of the Hayabusa 2 team, and a lot of my Japanese colleagues are on my science team. And you're going to get an exponential increase in our knowledge by having samples from two different asteroids, which appear similar in some ways and very distinct in other ways. So there's lots of intriguing puzzles that we're going to go in and solve across the two different missions.
Yes, so the science for the study of asteroid is very bright and it's going to be extremely interesting. And I would just to mention that for anybody who wants to start to study astronomy or to become an astronomer, do not neglect asteroids, because I think there will be a lot of major discovery coming from those missions. It will take years and years to analyze those samples, years to publish all these results, of course, right?
That's right. And actually, that reminded me, one thing I want to mention is we will be recruiting graduate students to start in the fall of 2022, specifically to work on sample analysis and the Osiris-Rex sample. So if you're in college right now and you're thinking about going to graduate school in planetary science, get in touch with us at the Lunar and Planetary Laboratory at the University of Arizona, because we're looking for some of the best students around the world to come and help us analyze this material.
Perfect. So what's the major kind of surprise for you? What's the moment when you look at this mission? And I'm sure it has been a lot of intensive moment for you, but if I ask you, give me an example of the moment for which you say, wow, this is amazing. What was it?
Well, we've kind of hit on some of the ones, but the one we haven't touched on yet that I think is the most exciting science result for me is we found carbon and we found organic molecules, but we also found minerals called carbonates. And not only did we find the minerals, but they're in large veins, like meter-sized veins and tens of centimeters thick, unlike anything we have in our meteorite collection. So my dream has always been that we're going to bring something back in the sample that is not represented in the meteorite collection. And these massive veins of carbonates, we don't have anything like that, which means we're going to get a whole new area of investigation in cosmochemistry. And that's my dream. And we saw it on the surface, and I got fingers crossed that some of that material is in the capsule on its way back to Earth.
All right. So one more question, I have two more questions. One of them is how citizen science can work on the Bennu data. Will you have a program for them, or did you have in the past a program for citizen scientists?
We did. We worked with CosmoQuest and we reached out to citizen scientists all around the world, and they helped us. I mentioned early on that the surface was really rough and rugged and rocky, and finding viable sample collection sites was a big challenge. And we engaged the citizen science community, and they counted hundreds of thousands of rocks on the surface and measured their dimensions for us. An amazing database. They also contributed to the sample site selection. We opened it up and we said, tell us where you think we should collect the sample. And actually one of the CosmoQuest sites made it to the final four as a viable site that we were investigating. And we actually did high resolution characterization of that. So we really appreciated the efforts of our citizen science, and it was a really valuable contribution to the mission.
Okay, I have one last question, Dante. First, thank you very much, Paula, for the stars. We just got them. Kudos, thank you very much. And the last question I have is, what's the future of the Osiris-Rex mission? Do you have extended mission? Do you have things going to happen with the spacecraft?
Yeah, so we are hoping, this is a decision that NASA still gets to make, but we have found a trajectory that after we drop off the return capsule in 2023, it's 6 years of cruising through the solar system, but in April of 2029, we can actually rendezvous with another asteroid, and a very famous asteroid called Apophis. And I was stunned when the team came up with this solution, because I had to ask, where could the spacecraft go after the primary mission was complete? And I thought for sure we'd be looking at flybys, but this is an actual rendezvous. We'll be able to go into orbit around Apophis, and we'll be able to do all of the global mapping like we did at Bennu. So it's an amazing, basically bonus mission. And for me, as you know, somebody who's been working on this program now almost 18 years, this is the future. So we're really focusing on personnel development, and I'm looking at the next generation to lead the mission into the future here.
Very nice. Apophis is a very interesting target. We try to observe it with the Unistellar network in occultation. We participated with citizen astronomers to this occultation campaign to refine the orbit of this body and hopefully get the shape and size for you to get ready for the flyby and the rendezvous. Sorry, because that's a rendezvous.
Yes. Thank you.
Okay. Well, thank you very much, Dante. That was an amazing conversation, and I would have loved to keep you longer. And I think I'm going to invite you to a SETI talk in the future to talk about all this fantastic result with the Osiris-Rex mission.
Sounds great.
Thanks a lot. Thank you very much to all our viewers. If you watch us, you know about us. We are the SETI Institute. We are a non-profit organization. We're here to talk about space exploration, the search for life in our universe. And as a nonprofit, we are counting on your donation. Donation can be making a financial donation, or it can be also helping us by following us on social media, by clicking here and here to make sure that you know when there will be a next SETI Live. We have one tomorrow with Nelly Benayoun, and we are going to talk about the International Space Orchestra. We also have the SETI talk in 2 weeks where we're going to talk about rocks, planets. So thanks a lot, everybody. Watch us, follow us on social media. Dante, I see you very soon, I hope, for one of our SETI talk.